No, it was prove or disprove. Okay. Which is so annoying for like a time crunch. Because it's like, I don't know. Like you think it's gonna be a disproof because I don't know. It included it, but it wasn't. It was true. It was proof that whether this is a group or not under these operations.
It sounds very simple. So,
We do so many of those.
but the one is like the group that you did this like was
It was the most like terribly. And it is in your like yeah, it was the final exam.
it was the first question.
It was the first question.
And it took up so much time to think.
Yeah. Yeah. He was nice. He was like, I'm gonna give you how many? 7? And you get to pick 5. He didn't like 2 of them. But see, the thing is that this question, everybody knew the concept. Everybody knows how to prove something in the group. So you're like, okay, I definitely know how to do this one. But then it was just like the most difficult. This is great. Yeah.
Both of them are the alumni here? Both of you?
Only one.
Oh, okay.
But they're both doing maths.
Oh, where?
The University of Rhode Island.
Where is it?
University of Rhode Island.
Rhode Island.
Yeah.
In America.
Oh, in America. Okay. So you're from America? Oh, I do.
She's one of you're one of
You were my examiner for my final project last time.
Which topic?
the tiles, right?
The music
Oh, the music.
music generation by
Yeah. That was really relatively new that time.
Yeah.
Okay, cool. So you guys are doing master or what?
Yes.
Master? Okay. Which area are you guys like?
It's like graph theory, probably graph theory. Everybody, it seems like everybody is doing ramp, something ramp.
Oh, it's in your department, you mean? Or
It feels like I don't know. I've seen a lot of research.
I think.
And it's kind of
Yeah.
I like stuff that's easy to understand conceptually and hard to
Right down.
yeah.
So you guys come back for holidays or?
Yeah. It's a summer
Come
holiday.
on,
So 不重要，你是不纠结。
Yeah.
Not really, because it's still reading the stuff.
Sure. Okay. So you mean won't include the new stuff? Huh?
No.
Yeah, sure. Maybe we can comment a little bit on you. Yeah.
The notations there are really a bit confusing.
Which part?
They use the physics notation, the Einstein notation, superscript, subscript, that one.
Oh yeah. But then
Really confusing, that one.
yeah, I mean like you mean the 6J symbol stuff? Huh? The J symbol.
J symbol.
But my point is, you look at the bird track.
Yeah.
The diagrammatic is more important.
Yeah.
The calculus.
To read that part, you need the stuff.
Maybe you can treat it as a tool first.
Okay.
Yeah. Instead of like seeing where they came from or what. Yeah. Those are tensor stuff. I guess what you mentioned. Yeah. Those things will represent some tensors. Yeah.
Okay.
That part is not very important. What we need is the calculus of that thing. So basically, how to calculate using the and then the paper I show you is to make them what they call it, Hermitian one, so that if you rotate 180, still the same thing. Yeah. So good thing about it is no matter you put cross at the top or bottom, they should absorb similarly. Yeah.
Okay.
Like that. Right. Have you figured out the operator already, the Hermitian thing?
Nope.
No?
So
This past week I just look at the cancer things.
Tensor thing. Okay.
Yeah.
That one is not very important for us.
Yeah. Just quickly go through.
You can quickly go through. Don't understand also never mind. Yeah. When you go into the more important is the diagrammatic stuff. And then there's bunch of equation they prove by yes. But then we want to develop it for the Hermitian one, the general Hermitian.
Okay.
Yeah.
Do you also last time you read the paper you also skip the things?
You mean the book? Book checkbook. The tensor stuff like that. Kind of skip lor. Because for us it's like not important for our calculation. Yeah.
Then the
Because we already passed the period of like learn. I mean, how to say? We are beyond that already. The topic is already beyond that. We already start looking at the diagrammatic category. Yeah. So it's not like I want to know how this diagram, why we need to consider this stuff, and then why do we care about that? But then obviously, yeah.
like those notations you already
Because
used to already.
we won't use the tensor thing.
Oh,
We're not using tensor stuff. We already abstract it to the diagrammatic stuff already. So we just stay in the diagrammatic world.
So like
It won't-
technically don't need that one.
Technically don't need, yes, that's right.
Okay.
But obviously that's where why they want to consider this diagrammatic thing. Why they turn to look at this thing. Because they need to solve some tensor stuff.
Shanghai, Chengdu.
China is related.
How did you hear about this university?
Actually, it's because it's summer.
Yeah.
It's included in our Gaokao system. So I can just pass Gaokao and with my score to attend. But I didn't apply here. A lot of people said, "Oh, why you choose to study this here?" I was like, because my score, I just got the score and I can't.
Yeah.
But you don't find possible this.
20 years.
It is my thing. We're just here for support.
You have a lot of
Is Darren coming? No. You representing him or you just come on yourself? Okay. Who else coming? Dooley, right? Change to Dooley already for masters. Might not be here. Examiner Chris. Yeah. Darren said one is enough for the proposal defense. Okay. And then he said need 3 for the examiner. Huh? I don't know. He said I asked him because let me ask Chris.
I know, yeah. Every semester I have presentation.
You have a lot of projects. We only did one like in April of one course. And then students, we don't have the time. So this time. It's a big AI. I don't really. I don't know. It's you.
Yeah.
Probability, you know, the this is my third semester. I think this is they'll be syllabus in everybody. So this is my
Of course, yeah.
mathematics for like masters of
Yeah.
oh, that's so really cool.
Yeah. Sometimes it
AI has on the past in advanced
We used to have a lot of take home tests, and now we can't do that anymore.
and so you have to stay in the school for much longer. Okay.
Sometimes we have to present our homeworks to make sure.
Sometimes a teacher might just ask you to explain that.
You actually did it. Yeah.
Our university, I guess some teacher really like suggest us to use it.
Yeah, our teachers don't want us to use it.
Yeah, I know a lot of. I heard from one student who's from their university able to ban.
Yeah.
Well, this is so unique for me. Some
Teachers in our university also,
They're like, use it as a tool, but you have to understand everything.
at the end, it's like, they cannot totally ban. It's also up to you to make sure you.
On a lot of times.
Yeah.
It's
I don't know about-
so.
I don't know about now, but
No, it is. Yeah.
so you still need to know things. It might help you. Or like, higher math at university. So,
My parents code a lot of AI stuff. Yeah. Yeah. He's doing.
But no one is a university. So
now we go to the University of Rhode Island.
It's a smaller.
It's in
I don't know which state it is in.
Rhode Island. It's like,
New Hampshire.
yeah, it's America, like this.
Start soon.
It's the year in New York City.
I think the recording start already.
Other side of the world.
Okay.
Yeah.
So welcome everybody to Joel's master thesis proposal defense. We got few visitors here. Right, we got Joel's friends. Yeah, all the way back from US. Okay. And then we also have Francis. Okay. Francis. Okay. So we are, our examiner is here already, so we can start. I guess you just click this one. Yeah, just this one. Okay.
All right, so thank you everyone for coming. So this is going to be my proposal defense. I think the general flow is that I'll have 50 minutes of presentation and then we'll open for 10 minutes of Q&A. So this is my title. Our goal is to develop basis theorem for the two morphisms of Heisenberg category. So this is going to be the general flow of my presentation. I'll see how it goes. We should be able to cover the first three of it, and then maybe we'll talk about the fourth one. And as a remark, this category, the quantum Heisenberg category, is only closely related to what I'm going to say, because at the time that I was creating this slide, we kind of found a new category that is actually what we are supposed to talk about. So, but then it's still closely related. So I'll tell what's different when we have time to go over it. Okay, so let's start. So the main thing that I'm going to talk about today is about the Heisenberg algebra, and as independently established by Nakajima and Groshnowski, the Heisenberg algebra acts on the cohomology space of the Hilbert schemes of points on surface S. So why is it that it's important for us to study the Heisenberg algebra? Is because it has links between Lie algebra and also geometry. And so, given that importance, in 2011, Licata and Kautis successfully categorified the Heisenberg algebra. In this talk, it's specifically called the lattice Heisenberg algebra. For your information, Licata is also my supervisor's supervisor. So, fun fact. All right, let's talk about the Heisenberg algebra. So let's assume that K is an algebraic closed field of characteristic 0, which is also not Z2. So let's consider a finite subgroup of SL2K. And we denote the two-dimensional representation of gamma by V. So think about K2. And the representation just says that we have an action of the finite subgroup on V. The standard two-dimensional representation just is the matrix multiplication. So the action is matrix multiplication here. And by the McKay correspondence, the finite subgroup are associated with the affine linking diagrams with vertex set I of gamma and edge set E of gamma. What that looks like is this one. So mathematicians have successfully classified all finite subgroups of SL2K. They look like this. The cyclic group, and all the binary something subgroup. And then McKay correspondence is basically the correspondence between all the finite subgroups of SL2K and all the affine linking diagrams. If you're interested, how you obtain those diagrams is you take each node as a irreducible representation of the finite subgroup, and then you calculate dimension of some Hom space between them. And it turns out that the number of edges between them just corresponds to the dimension of some Hom space. Okay, so this is how we get the correspondence. And then we are going to introduce some quantum carton metrics. This is just to make things easy. You don't have to remember them. It's basically a matrix whose entries are these symbols. And it basically tells you that it tells you the connectivity of the edges in the affine linking diagrams. So let's say if you have the same nodes, it gives you the entry t plus t minus 1. And if they are different nodes but they are connected, then it gives you -1. And if they're not connected at all, then it spits out 0. So for example, this one describes the connectivity of the affine thinking diagram for the cyclic group of order 4, also Z4. Okay, so now we can define what's a Heisenberg algebra. It's a lot of stuff. We can go through a bit of them. So the Heisenberg algebra is defined to be the unit cell, which means that it has an identity, KT minus 1 algebra. So just think of a ring with scalar multiplication generated by these two generators, each for I in the nodes set, and then for each integers n greater than 0. So then it looks a bit overwhelming, but then you don't have to memorize all these relations. You can basically summarize. If you notice carefully, 1 and 2 describes the commutativity between the P's, commutativity between the Q's for all Mn and Ij. And then the last 3 of it is to describe the commutativity between the Q and T, varying the I. So if you have the same I, this is what you get. If you have different I, but then they're connected in the diagrams, then you get this. And if they're not connected, you get complete commutativity. So then it's basically just the two relation talks about commutativity between the P's, commutativity between the Q's, and then the last 3 is just commutativity between P and Q. So if you don't want to remember all this, it's just basically an algebra defined by generators and relations. And the relations are just basically commutativity between them. Okay, but instead of the algebra H of gamma, we're actually going to consider what we call the idempotent modification of H gamma. So this is make H gamma a category. So what we do is we split the unit because it's a unital algebra, so it has an identity. You split the unit I1 into this orthogonal idempotence indexed by Z. And what that means is just that if the index are the same, then you times them together, you just get back the same thing. That's the idempotent parts, and then these two combined together is the orthogonal part. So then, what's this idempotent modification is? It's a KT T minus 1 linear category. Linear category just means that its home space is a vector space with objects, the integers, or the idempotent itself. You can basically identify the idempotence with the integers. And an arrow, n to m, is of the form 1x, 1m, where x is an element of the algebra. So then we are going to impose some relation to our category as well. These are the relation. So if you want a concrete way of thinking about this, you can think of this starting at some state k, and then this p will raise the state k into k plus m. So this tells us which state we are in, and this tells us that what state we are going to be after we can raise. And q will do the opposite by decreasing the state. So not really a mathematical way of thinking about it, but it's a concrete way of thinking about it. So the relation in the idempotent modification are directly inherited from H gamma. So for each k, we simply just add a 1k to both sides of the original defining relation. For example, this one just corresponds to this relation. So we just add in the 1k at the back. So then we do it for all of the relation, and then we actually just get back the same relation. So, and you can notice that it doesn't depend on which k. So if you just swap in any of the integers there, you still get the same thing. I mean, you get the same type of relation. And so the defining relation for this category is somewhat the same as our algebra as well. So we can abuse the notation slightly, but denote the idempotent modification by H gamma as well. And it should be clear from context as well when we talk about either the algebra or the category. So then, since H gamma is already a category, or generally it's one category, so then in order to categorize this H gamma, we have to consider a two category. So now we are going to construct a category that is introduced by Kaplan and Kautis, which categorifies the Heisenberg algebra. I'll talk about what it means by categorifies that later. So to do this, okay, since gamma acts on V, the matrix multiplication, it also acts on the exterior algebra setting. The exterior algebra is K, direct sum V, wedge V. I cannot write anything now, but that's what that is. And so we set B gamma to be the semi-direct product of this and gamma. So we just created a larger algebra with the exterior algebra sitting inside of B gamma and also K of gamma sitting inside of B of gamma as sub-algebras. Then what does this B gamma look like? An element of this is just a linear combination of the ordered pair V gamma, where V is in the exterior algebra and gamma is in gamma. And the multiplication in B gamma is given by this. Since with an action here, so this one also sits in the exterior algebra, and then once you wedge it, it's also in the exterior algebra. And then the right side is just usual matrix multiplication. And so you see that whole thing at the right actually sits in B gamma as well. So given this multiplication, it defines you can basically prove that this B gamma is an algebra as well. So then if we have a basis for V, then B gamma as a finite homogeneous basis given by this for each gamma and big gamma. Homogeneousness means that each of them have a certain degree. It has its own degree. It doesn't consist of multiple degrees. Okay, and now we are going to introduce the trace map. The trace map is basically a generalization of the trace in matrix. So the natural Z grading on this one basically just means that it can decompose into a direct sum of C star. And then it extends to the grading of B gamma by putting K gamma in the degree 0. So for example, right here, you just basically reads this as degree 0 and reads the whole thing given by the degree of V1. And also this one, you read only the degree of V1 wedged with V2. We denote the degree of homogeneous element by the absolute value of B. And then here is the trace map that we want to introduce. We basically just spits out 0 for all the degree less than 2. element, homogeneous element, and then this one depends on what the gamma is. If the gamma is 1, then we'll give 1, otherwise it's 0. So the trace here we introduce is slightly different than the in the trace, the matrix trace that we know. Because in the normal trace, we have trace AB is equals to trace BA, right, for matrices. But then now we have an extra thing here, an extra thing that depends on the degree of A and B. And we call this, instead of being like actually symmetric, we call it supersymmetric. And it has to be non-degenerate as well. Okay. So all the algebra out of the way, we can introduce a category, a two category actually. Okay, let's define an additive k-linear z-graded 2 category as the following. Objects are all indexed by the integer z, as in the same as in the idempotent modification, and then the morphisms are generated by these. The p in is something that's a convention, I guess. Diagrammatic form of p is just like an up arrow, and then q is a down arrow. And basically, a general one morphism is a finite sequence of p's and q. So a one morphism can look like up, down, up, down, up, down, up, and so on.
You should have drawn it, right?
Yeah. Yeah, I should have drawn it. Right. And the identity one morphism is the empty sequence denoted by that thing. So what would the two morphisms be? Because we are in a two category.
Oh, yeah. We got the picture.
This has the two. Okay, so just to remind everyone, a two category is basically just it has a two morphisms, which is morphism between the one morphism between morphisms. It's basically a two category is basically its object and one morphism is a category, and also it's two morphisms and the one morphism form a category, basically. So then, what would the two morphisms be? It's literally these type of diagrams. So we can, I should draw it.
Label.
Huh?
Label. Label in the source and the
Yeah, so because the domain is like the sequence up, down, up, down, up, down. So the same, for example, this one, identity of two morphism, is actually up to up arrow. It's an identity from up to up. And that one is an identity from down to down. And we also have these dots. And these dots are labeled by the elements of B gamma. So the algebra that we talked about just now. And if you want to be really precise with what these diagrams are, it's basically the diagram are these things. They're called they are one manifold, compact one manifold. So basically just some strings. And then they're immersed in like the r times 0 to 1. And you can basically to move the strings around, you can kind of like pull it there also. That's called planar isotopy. So it just means that if you pull it around the diagrams, they're still the same thing. So that's basically what a diagram is, and also define two morphisms between the one morphisms. And let's talk about the local relations that we want the diagrams to satisfy. The dots, the algebra of the dots are dictated by the algebra of the B gamma. So multiplication or collisions of the dots would look like that, would be the multiplication in B gamma, and addition would basically look like that. Just merge the two dots together. And if you have a row of dots, you can super commute with two dots can super commute with each other, which means you flip them, you're going to introduce some sign difference between them. You cannot really commute freely without introducing some factor between them. Okay, another relation is that dots can slide in the diagrams. So this is a morphism from up to up. That one also. And then you have the cups. The cups is it's a morphism from the empty sequence to down and up. And so the relation is that dots are able to slide between each in the string itself.
So before adding in the dots, you have these relations between crossings and like cups and caps. I guess you call. So those are relations you do have. Yes, so that's how you present them. Because you didn't actually like very briefly maybe you mentioned it, but before talking about local isotopy, so you do have these, right? That's why you need local isotopy. So
yes,
these all match up. Yeah.
Yes.
Just wanted to check because then you add on the layer of dots.
Yeah. Yeah. These diagrams are already inside.
Yeah, they're part of the definition of the space.
Yes. And then,
these two, yes.
Yeah, and these relations as well. Not going to go through all of them, but the first line is basically you can, in the middle, you can see that you can slide them in between the crossings.
Great.
Yeah.
Find them.
Yeah.
Yes. So I should remark that these are not in diagrammatic stuff, diagrammatic category. These relations are not they are not naturally satisfied. These are just the relation that we impose. So we don't actually have them naturally. So going this relation also, so to remind you all, sliding of dots, and then this bunch of relations. The grading, I think I'll skip this one. So what's the category that we are interested in? It's this one. The H gamma will be the Caribbean envelope, also known as the idempotent completion of H prime gamma. So the objects will be indexed by Z again, but now the morphisms will be paired with the idempotents, endomorphisms. So R is still the one morphism, so it's still the up, down, all that sequence. And then two morphisms is a diagram that satisfies some additional stuff. So instead of just looking at any diagrams at all, we have to look at diagrams that satisfy some conditions. So this is the Kirby envelope of H prime gamma, and this is exactly the category that was introduced by Ikata and Curtis. And so in the same paper, they proved this result. This is exactly what it means to say that K gamma, the H gamma categorifies the Heisenberg algebra. So they prove that there's a canonical isomorphism of algebras between the Heisenberg algebra and the Grothendieck ring of H gamma. So yeah, this one is the proof. This is the result that says it categorifies H gamma, but we're not interested in this one. And here is my problem statement. So whenever we have a linear structure, linear stuff, vector space maybe, we're always interested in their basis, I guess, because you're able to describe something in terms of simpler things. So that's why this is what we are interested in, given any two morphisms, one morphism, x and y in H of gamma. Our goal is to determine a basis for the home space. Yeah, that's. Do we have time? Okay, since we have time, I'm going to talk a little bit about the quantum Heisenberg category. So I'm just going to go through quickly what this category is. So with a background, so recently, these three authors, Brennan, Savage, and Webster, introduced a more general category.
This is Heisel and Webster. Webster.
Oh, that's
Yeah.
Huh? Oh, okay. TER. My bad. So they're going to they introduce this general category, and depending on what the parameters are, this category already appear in literature. For example, if you sub in k equals to 0, is the affine home-fly PTs in category studied by Brundan in a paper. I don't know anything about the category, but it's just to show us that it's not something new depending on the parameters, but in general, given any parameters, it's quite a new category. So why we're interested in this category is because given a specific parameters, it's closely related to the H prime gamma that we introduced, but not the Kerobi envelope. So yeah, quickly go through. We construct this category by starting with a simpler category. So we start with AHZ, which has one object, which is up. And then we're going to introduce two generators, the dot and also the crossings. So this is what I was talking about when you have morphism between up to up, it means that one. And so it has to satisfy some relation also. I'll go through this quickly. So this relation indicates that tau is actually invertible. Our crossing is actually invertible. Because if you move around the things, you distribution and stuff like that, you can see that defines a two-sided inverse of tau. And we also require the x to be invertible. So we introduce another generator called x inverse. So these are the diagrammatic forms of our generators. The crossing is this. Note that in this category, you can notice that there's one string above the other. So in some way, orientation matters in this category. And x is, the dot is x. So what's different here that I mentioned earlier is because, as you have noticed, that the dot is actually labeled by z. But our dot in our category that we introduced just now is labeled by the elements of B gamma. So we actually found another paper. It introduced what is called the Frobenius Heisenberg category, which actually have the dot that is labeled by B gamma. So then, but I've not read enough in order to present it. So this will suffice. So you just imagine the x, the dot being labeled by B gamma. It's closely related to the one we introduced. So this relation have a diagrammatic form like this. So you can already notice why we are interested in this type of category, because the diagrams look very, very similar to the ones we have. The dot siding, and then this thing. Yeah. To construct this quantum Heisenberg category, we introduce a right dual down arrow, which is the Q just now we saw. And this is just monoidal category stuff. You introduce a right dual, you have to introduce some cups, they're called units per unit, which satisfy some axioms. So we will introduce these right crossings just to make things easier, and then downward dot is defined as this. It's just basically a composition of so one dot here and then a cap and a cup. Okay. We also have this relation, the dot sliding the cups. So very similar to the category that we have just now. And we're going to consider this thing. Just a fancy way of presenting it. What we're interested is in basically are the entries of these matrices. So what is at high KZT is basically we allow objects to be able to direct sum each other, and then we change its morphisms into these matrices. We're just interested in the entries, so this one is just a fancy way of presenting it. So the idea is to introduce the quantum Heisenberg category is KZT is the strict K-linear monoidal category obtained by the simpler category we saw just now by joining the right dual to the up arrow, which is we introduce the cup and the cap, and together with the matrix entries that inverts all these matrices. So we're going to forcefully invert the matrix by introducing these symbols. Doesn't really matter. Why I say it's a partial definition of the quantum Heisenberg category, because you have this thing, you have all the entries of this matrix, and of course you must have some relations. And the relation is kind of long, so I'm going to skip them. But what is interesting is that they actually prove a sort of basis theorem for this category for any k, z, and t. Actually, for the k would be nice enough. So for any grounding k and parameters, set t in their units and objects x and y. So the up arrow, down arrow. In this category, the morphism space is a free right sim tensor sim module with basis theorem. Free just means that it admits a basis as a module, and this one is a ring of symmetric function. And this set is basically consists of much simpler diagrams. So the idea of proving this theorem is that they're going to prove a lot of relations in the category, and those relations are basically straightening algorithms of the diagram. So given like a very, very complex diagrams, you are going to use these straightening algorithms in order to decompose these very complex diagrams into very, very simple diagrams, like linear combination of the simple diagrams in here. And then for linear independence, they're going to use some big machineries from category theory. So that's basically the thing. So you can either use the idea to develop our basis theorem using the work that they have done, or I think now we are trying an approach of purely calculation, right? Yeah, so we have 2 routes time. We see, like, depends on how things go. We'll see how we try to develop the basis theorem. So yeah, so for me, thank you very much. Any questions?
The last slide. Right. So this is for the quantum Heisenberg category, right? So
Yes.
what you're doing this is for the Heisenberg category that there. Do you know how these two what parameter we need to set T to, for example, to get back to the
Yes. We actually found those parameters in our discussion, but right now I know the K is like -1 and the Z is something, Z and T is something else. Yeah, we'll be fine.
as long as you know. But of course, this isn't really quite what you want because the dots. Are not-
Yes.
But yeah, the Frobenius will probably give you. But is there a basis theorem for the Frobenius?
Yes. Yeah.
So there is. Yeah, there is. Who wrote the paper?
It's same people,
Same authors? Yeah.
Yeah.
Is it in the same paper?
not the same people.
Same paper. Like, how long ago was this?
The Frobenius
Yeah.
one is like 2-3 years ago.
Yeah. Okay. So it's very, yeah, it was very.
Yeah,
Maybe it's I haven't read that paper.
but it's more complicated because that one you need something called super categories
Yeah.
and not just the regular 2 categories of
Super categories are not that much.
I guess.
Depends on that. Yeah. Super in this context just means a Z2 grading.
Yes. Yeah.
So it's like how quantum really just means a Z grading.
Mm.
There's nothing too mysterious. A little bit, not too.
Mhm.
Yeah, Webster was supposed to be my supervisor, but
Oh.
I worked out there.
Let's see.
He moved to Canada.
Yeah, you moved to Canada.
Yeah, that's right. About the time I was constituents. We were already kind of talking about potential projects. But anyway, sorry, not to derail this. History. Yeah, I don't really have any option for you.
Okay.
But I'm interested to see what turns up.
Okay. Thank you. Any other questions?
Audience want to ask. What's the use of this project?
Something you don't ask. True applications.
Application.
I mean, one thing.
Yeah.
Okay. So at the very beginning, you said this is funny. You said here is characteristic zero field, which is not Z2 but
Yes.
characteristic zero already means not
Yeah.
Z2. So is there anything about positive characteristic in here?
Is there anything
Did
about
it,
positive?
yeah, is there because that sounds like a language to put if you're considering positive characteristic.
Mhm.
So for your talk, that's not necessary, especially for first case, you don't need to think of positive characteristic. But did the papers mention anything of positive characteristic?
No.
Because yeah, certain strange things happen in categorification for the characteristic, but it
Oh.
also makes it more interesting. So that's
Oh,
probably a PhD project if you want to go further into that. It's like think about the positive characteristic. Because that's modular representation.
Yeah.
oh.
That's what Jody Williamson.
That's probably what he, yeah. And that again, I'm not sure how this relates to the symmetric group, but that symmetric group in a characteristic P, which is still many open problems.
I see.
The reason that like you're not a feedback.
Yeah, so because characteristic zero
Uh,
already covers that. It's probably because at some point someone said like positive characteristic but not characteristic two, and there's a more general situation where some of the things you're defining applies. Like you can define some of these for both characteristic positive, like Heisenberg algebra.
Hmm.
But except for characteristic two, because you don't want plus to be negative.
Yes.
But
he said.
it doesn't apply to what you have. It's probably like leftover from something. Like positive characteristic.
Oh yeah, Z2 treat negative and positive the same.
Yeah. So
If
lots
you
of things
want
to
negative, then yeah, correct. Maybe negative appear in the relation, then you need to like treat it differently. So you have a different treatment.
Okay.
Yeah, actually, minus sign is very important here. I was like get stuck with a lot of minus signs when I first doing the
very
calculus.
PhD paper about minus sign that's and what was it?
Yeah.
Minus sign that exists but that I didn't know, but now I know why it is there. Or something.
Yeah.
That's just a typo.
And, Yeah.
And also even even super commuting. That's your trace super commutes.
Yes.
That was actually that is something that I kind of would be curious about now then because this hints at like as you said super categories.
Yeah.
But wait, my previous work involves this.
Oh,
So that's why
I see.
a basis theorem.
then maybe we can ask you.
Yeah, that's it.
Yeah.
No,
What do you mean by ground? What do you mean by ground?
It's just I think it's just a language thing. It's just it's over the ring.
Like base field.
Yeah, that's something.
you see this a lot when yes, actually not that. But yeah, it's like the base field. But you also see this sometimes for like graded ground, it's like level 0.
Oh, okay. That's
Here are things are very often graded.
Actually, this project is supposed to be diagrammatic.
Yeah, it's supposed to be
I
Suppose-
hope,
yeah.
I hope it will still sound diagrammatic for you because hoping the basic theory from algebra is painful.
Actually, the technical thing here is called the tick calculus.
What?
Tick calculus.
What is that?
Tick is like ting and tick. T-H-I-C-K.
okay.
Yeah, yeah. So he's doing Kirby envelope thing, right?
Right.
So it's the idempotent. So idempotent would look pretty thick.
Yeah, yeah.
Yeah. So he like put a bunch of string
Right.
together.
That is what the cutter, yeah.
Yeah. So you can think of the young idempotent,
Yes.
symmetrizer and anti-symmetrizer. So you have a bunch of these what do you call them? Not transposition, but the elements of symmetric group.
Yeah.
So you take a linear combination of them, they will be satisfying E squared equals to D. So
Yeah, the
yeah.
thing is, idempotence, Theorem envelope is so that your category is enough projectives. That's the main thing. It's like put enough,
right.
enough projective
Right.
material. So that all the nice things you want, those types of categories. That's what the completion does for you. But yeah, you see this in like quantum groups too. The quantum groups you need to figure out the prediction for it to define the basis.
Yes.
Same situation.
That's right.
So you're on the right track, basically. But my general feeling, basically.
Yeah, this Heisenberg algebra actually is the positive part
Oh, yes.
the what do you call that? The vertex operator algebra.
On like a very simple case, right? On like one
Yeah.
something. I forget the
Level 1
Level one,
representation.
yeah, that's why already here you see the outline by instruction.
Yes. Yeah. Okay. Any more question from the audience? If not, thanks for coming. Yeah. Thank you for coming.
So